All right, so in this video, we are going to be looking at the surface area of our helix with the elliptical cross-section using two different methods. Now, since the previous video, I changed a little bit. I increased the number of ellipses throughout the helix, and then also increased the divisions of theta to increase the resolution with each helix a little bit. Got rid of the legends over here, and then changed the color to pink as well. Now, the first method that we're going to be using is going to be looking at the differential area of the surface area that we've created with these ellipses. So if you zoom in, each of these little divisions that we've created looks like a parallelogram, and we can calculate the area of that parallelogram by doing the cross multiplication of the differential of the vector of the surface vector in the t direction through the length of our helix, and also in the theta direction around our ellipse. So the first thing that we will do is do a delta t, which is going to be our division of the arc of the helix, t1 minus ts 0. We'll do the same with theta, delta theta equals thetas 1 minus thetas 0. And the next step will be to look at those differential vectors in the t direction and in the theta direction. So for that, we'll look at our surface function, and we will take surface jack and take the Jacobian of our surface function with respect to those two parameters, 0 and 1, corresponding to t and theta. We'll define a new function called surface dA, or surface differential area, inputs as t and theta. We'll do surf jack. We'll do a dv dt and a dv d theta equals, there we go, surface jack of t and theta as well. And we will return the cross product of these, jnp dot cross, to find the area of the parallelogram between those two vectors. So dv dt, just that differential change, times the length of that vector, delta t, and then dv d theta times delta theta. Now, because this is just taking a single instance of t and theta and finding that area of that corresponding parallelogram, we'll do the same as what we did earlier. Return equals, oops. We'll do the same thing we did earlier and take advantage of Jax's vectorization capabilities. So we'll define a new function that's surf dA for differential area, vectorize, which is going to be equal to jnp dot vectorize surf dA, surf dA, and our signature is going to be two scalars for t and theta, going to another scalar, just that area of that parallelogram. And then lastly, we will add up all of those for our entire set of t's and thetas. This will look kind of similar. Let's see. T's and thetas. And we'll do that same broadcasting that we did before, but instead we'll take 1 minus off of that array that has the number of t's and the number of thetas, because we don't want the number of posts, we want the number of fences in between. None, and then this will be none, comma, colon, minus 1. Looks like that's an O instead of a 0. There you go. There we go. And the resultant area for using this method is just a little bit over 458. The second technique that we're going to be using to calculate the surface area of our elliptical surface here is by multiplying the arc length of our central helical curve by the perimeter of our ellipse. We'll start with that central arc length, and we'll define helix dv dt, where v is the position vector of a point along that curve. The derivative with respect to t, so the Jax dot Jacobian of the helix function, 0 to point towards t. And we will define a function helix d arc length at some position t, or some time t. And then we will do helix return jnp.lin norm, because we want the length of that curvature. We'll do helix dv dt, so we'll evaluate that at 0 r mz, and then multiply that times delta t. Because this is, again, just a single instance of this equation for the arc length at some t, we're going to, again, use Jax's vectorization capabilities. We'll define a new function, helix d arc length vec equals jnp dot vectorize helix dot underscore d arc length. Our signature is equal to just one scalar to another, because our scalar t turning into our scalar of that arc length. And then we'll do jnp dot sum helix d arc length. Oh, I already see one error. Got an H there. Arc length vec for all of our values t. Alright, so what we find is that our arc length of that central helical curve is just about 94 units. Now I'll copy and paste this because we're going to do something very similar to find the surface area, not the surface area, the perimeter of our ellipse with those little segments. So I'll change out some of these function names. So we'll do ellipse dv dt, Jax Jacobian, and instead of the helix, we're going to use the surface function. We're going to do 1 so that we look at the theta parameter. So we'll change that here as well. Delta theta, ellipse, d arc length vec. Can do the same thing. We'll vectorize it for all the values theta around that elliptical curve, or elliptical perimeter. And we'll do thetas. All right. That number looks a little bit high, so let's take a look and see what we missed. Oh, helix, there we go. Ellipse. Alrighty, so now we found that the approximate perimeter around our ellipse is just about 4 units. So let's see if we multiply the arc length of our helix by the perimeter of those ellipses, see what we get. there we go, and 458 and change, which is pretty similar to the differential area method. This method, the arc length times perimeter method, results in a number that is a little bit lower, and that would be to be expected because as we stretch our pipe around, we do stretch the outside, the very outside surface, all the way along that curvature, so that results in a little bit of error here. But as we can see, these two methods of differential area and then our arc length times perimeter method resulted in very, very similar answers for the surface area of our helical surface. Thank you.